This section is about, 1.6 is about rational expressions, and rational expressions are not polynomials. A rational expression is a quotient of two polynomials. So I've got one here for an example. There's a polynomial upstairs and a polynomial downstairs. They're both trinomials. They're both x squared leading term. Even their leading coefficients match. But we cannot cancel these. They're not factors. They're terms in the numerator. Well, it's a term in the numerator, it's a term in the denominator, but it's not a factor. What we need to do in order to simplify this expression is factor both of those polynomials and then remove the common factors. So I'm going to rewrite it like this. So the numerator is it's a trinomial with leading coefficient 1. We just have to factor this number, 16, into the two numbers that add up to 8. So the factors of 16, 1, 2, 4, 8, and 16. It's 4 times 4, and 4 plus 4 is 8. So this is x plus 4, x plus 4. If you need to do scratch work or a table to get there, that's fine. That's what scratch paper is for. But let's get through the factoring the denominator now. It's again, it's x and x give me the x squared. I really just need to factor this number into two numbers that add up to this number. 28 is 2 times 14, but 2 and 14 add up to 16. 4 times 7. 4 times 7 is 28. And 4 plus 7 is 11. So those are the numbers, positive 4, positive 7. Now you can see when it's in factored form that there are common factors between the numerator and denominator. They both have a common factor, or they both have a factor of x plus 4. I can cancel those or remove them, and what's left is x plus 4 over x plus 7, and that's the simplified form. So it's not by canceling the x squareds, they don't cancel like that. When we factor the polynomials, we can then remove those common factors, canceling the correct way. Multiplication and division. All right, so in this section, we're going to do this from time to time, the simplifying thing, but we're also going to look at how to combine rational expressions, just like we did with polynomials, how to add, subtract, multiply, and divide them. We did not divide polynomials, and we probably aren't going to do that, but we added, subtracted, and multiplied them. We can actually divide rational expressions pretty easily, and in fact, a rational expression suggests division anyway because it's a fraction, the thing on top divided by the thing below. So first though, we're going to look at product of rational expressions. And to do this, you need to keep in mind that since they're fractions, rational has the root ratio, and a ratio is a ratio and a fraction are the same thing in math. They're very similar otherwise, but for example, x squared plus 4x minus 5 divided by 3x plus 18 times 2x minus 1 over x plus 5. So product, we're multiplying. This is a rational expression, this is a rational expression. Let's, well, to do this, I just need to, it's multiplying fractions. I just multiply the numerators and multiply the denominators. Not too bad. But I want them in factored form. So as I write this whole expression as a single fraction, I'm not just going to rewrite it like this. I'm going to write x squared plus 4x minus 5 as, I hope this factors, factors of negative 5 that add up to 4. Yeah, they're positive 5 and negative 1. 5 times negative 1 is negative 5, but also 5 plus negative 1 is 4. So that's the factored form of this one. This one, nothing to factor. There's no common factor. Now, I just wrote those as one numerator because I'm going to multiply the factors of the numerator and the factors of the factors of the numerator and the factors of the other numerator to get the new numerator. Here, same thing with the denominators, but this one, these two terms have a common factor of 3. And if I factor that out, what's left is x plus 6. 3 times 6 is 18. 3 times x is 3x. This one, nothing to factor there. It's just x plus 5. But now that I can see these terms, I can recognize the common factor of x plus 5. And what's left is x minus 1, 2x minus 1 over 3x plus 6. And that's actually the best way to leave it. Factored form for these. If you wanted to multiply them out, you could, but this is good. This is fine. If we had to work with it again, we would have to factor again. So I like to leave it factored. The next topic in this section is I'm just going to say dividing. We're finding quotients, yeah, but a rational expression is already a quotient. I'd rather emphasize that we're going to divide one by another one. Again, though, let fractions guide you through this. So if I have 2x squared plus x minus 6 over x squared minus 1 divided by x squared minus 4 over x squared plus 2x plus 1. The thing to do with fractions and division is to multiply by the reciprocal of the divisor. So before I do any factoring, I'm going to rewrite this as 2x squared plus x minus 6 divided by x squared minus 1 times the reciprocal of this guy, x squared plus 2x plus 1 over x squared minus 4. Now I'm ready to do some factoring. It kind of helps that these bottom two are both difference of squares in form. I don't actually remember how I did this. I think I made a few notes to do this, but 2x squared plus x minus 6 factors with a 2x and an x for the firsts. But it's not the factors of negative 6 that add up to 1 that I'm looking for. It's really the AC method. I use 2 times negative 6 is negative 12. And then I factor that number into 4 and negative 3. Those are the things that I need to group to finish factoring this. But it comes out to 2x minus 3, x plus 2 for that one. Let's go ahead and do the rest of the numerator because I'm going to combine these into a single numerator of products. This one is straightforward. This is a leading coefficient 1, so it's x and x. The multiples of the factors of 1 that add up to 2 are 1 and 1. The denominator is where I can really take advantage of, in two different places, difference of squares. X squared minus 1 is x plus 1, x minus 1. And x squared minus 4 is x plus 2, x minus 2. Now I look for common factors. I see an x plus 1 and an x plus 1. Also an x plus 2 and an x plus 2. That's it. That's the only factors that'll cancel. So let me write my final answer up here. When I rewrite this, I get 2x minus 3 times x plus 1 in the numerator, and x minus 1, x minus 2 in the denominator. So that's the completely simplified quotient of those two original rational expressions. Next, we'll look at adding and subtracting. And since you're somewhat familiar with fractions, you can probably predict this. These are fractions. Multiplying and dividing fractions is pretty straightforward, across the top, across the bottom. Well, dividing, you gotta flip it first, but it's across the top, across the bottom. Adding and subtracting, we have to get a common denominator. So the process can be more complicated. It usually takes longer. So let's look at some adding and subtracting rational expressions. So I'm going to emphasize this again. To do this, we have to have a common denominator between the two rational expressions. If they have unlike denominators, they're not compatible and they don't add directly. You have to modify them so that they have the common denominator. Here's the example with numbers. So 5 plus 24 plus 1, 5 over 24 plus 1 over 40. I'm going to do this with the least common multiple. First of all, though, 24. 24 is 2 times 12 or 3 times 8. There's a lot of different ways to factor it, but there's exactly one way to factor it into prime numbers. A good way to think of that is 8 times 3. So 8 is 2 times 2 times 2. So my 8 times 3, that's 2 times 2 times 2 times 3. And I'm going to write it like that, 2 times 2 times 2 times 3. Next, 40. 40, you can use a tree to break it down into factors. It's got a factor of 2, 2 times 20. 2 is prime, but 20 is 2 times 10, and 10 is 2 times 5. So this is the prime factorization of 40. There's only one way to factor 40 into primes. You can put them in different orders, like you can put the 5 in front, but it's the same factors. Now what I'm looking for the least common multiple is a multiple of these numbers, a multiple of 24, so it's got to have all these factors. If it's a multiple of 40, it's got to have all these factors. And what I actually need is 2 times 2 times 2 times 3 times 5. It's got all the factors of both numbers, but no extra ones. I don't need, for example, I don't need 6 factors of 2. I only need 3 because they have 3 factors of 2. I need a factor of 3 and I need a factor of 5, but that's it. And that is an easy way to find this is my first number, 24 times 5. 24 times 5. Or 40 times 3 is another way to do that. Either way, it's 120. But what's important about that is the factors that it has and the factors of each of these numbers that they do not have. So what I want to do is multiply. This is the harder number, but it's first, so I'll do it first. I want to multiply this one. In fact, I'll rewrite this so you can see the original problem. And with this one, I want to multiply by 5 over 5. That 5 times 24 is 120. With this one, I want to multiply by 3 over 3. 3 times 40 is 120. So I get 25 over 120 plus 3 over 120, and that is 28 over 120. And then I still need to simplify. You can do this all at once, or you can do it in a couple steps. I see that they're both even, so I'm going to cut both of them in half. cancel a factor of 2 from the numerator and denominator. Here, they're even again, so if I do the same thing again, I get 7/30ths, and that's it. So this principle of adding fractions is the same type of thing that we need to take to rational expressions, only now our factors aren't just numbers. Our factors are going to be probably binomial terms. So let me give a simple example so we can see how this changes with variables. So in this example, we're going to do 5 over x plus 6 over y. The LCM, in this case, there's 2 denominators. Each only has 1 factor, though. This is a factor of x, this is a factor of y. They're not the same, so I need a factor of x and a factor of y. That's it for this one. No binomials going on downstairs. So what I'll do to this is multiply this one by y over y, and multiply this one by x over x. That way here I get 5y over, y times x is x times y, same thing, plus 6x over xy. And that has the same denominator, so I can write that as 5y plus 6x over xy. I've got another one that has a difference, but the process is the same. Addition and subtraction are both require the common denominator. In this next example, we're going to do subtraction. 6 over x squared plus 4x plus 4 minus 2 over x squared minus 4. And the first thing I need to do is find the factors. I have to factor these, but they're not just numbers. I'm not going to try and do it in my head or build an LCM just by writing it down. If you have to, you should work off to the side or somewhere else on the page on scratch paper or something to break these down to x plus 2, x plus 2, and x plus 2, x minus 2. This one's a perfect square trinomial, x plus 2 squared. This one is a difference of squares, a difference of 2 squares, factors like this. And the missing factor in each one, well, the LCM, I can now see the factors at least. My LCM is going to need to have a factor of x plus 2 and another factor of x plus 2. And also a factor of x minus 2. I'm not going to multiply that out, but those are all the factors. So I can use that with this fraction. I'm going to need to multiply top and bottom by x minus 2. In other words, multiply by the fraction x minus 2 over x minus 2. This one, I need to multiply by an x plus 2 over x plus 2. So here I'm going to have x minus 2, x plus 2, x plus 2. That's the LCM. Same thing here. Different order of factors, but it's the same factors. So let me clean this up a little bit. This numerator is 6 times x minus 2. And this numerator is 2 times x plus 2. But they have the same denominator, so I can just write them both over the common denominator as a single fraction. I could have distributed these coefficients in this step, but it's fine. We combined the 2 fractions into 1 fraction. Now I'm going to write 6x minus 12 minus 2x minus 4. I'm distributing the negative 2, not just the 2. So it's negative 2x or minus 2x, and then also negative 4 or minus 4. and that's over x plus 2, x plus 2, x minus 2. Next I need to combine like terms, and that's, I've got 6x minus 2x gives me 4x. Minus 12 minus 4 is minus 16. I'm going to write the x plus 2 as x plus 2 squared. It's a little more compact. And I'm running out of space. Finally, well, I have it as, actually I've been at one fraction since this step, but I have a single fraction here. I just need to simplify if possible. There's a common factor of 4 upstairs, leaving x minus 4. And then the denominator is x plus 2 squared, x minus 2. And I see no common factors. X minus 4, but not x minus 2. That's it. That's the difference simplified. And there's one more topic that section 1.6 covers. You need to see a little bit of. And that's called compound fractions. The book uses the word complex, but in the field of mathematics, complex means something different than complicated. And I like compound better as a name. You can call them complex fractions too. But it basically means that we have fractions with fractions in them. Either the numerator or the denominator or both are fractions. Here's an example where we'll simplify y plus 1 over x over y. So first with this, the fraction in the numerator is the first big issue here, because I can't just do multiply by the denominator. I mean, you can, but it's not a fraction. It's an expression that contains a fraction, but it's more than that. I want to make this into a single fraction. So let's isolate y plus 1 over x and write that as, it's really one step to do this. I'm just leaving some space here. I need to multiply by x over x to get xy, because this is y over 1. Y as a fraction is y over 1. Multiply the numerators, x times y. Multiply the denominators, 1 times x is x, plus 1 over x. Now they have the same denominators, and I can write this as xy plus 1 over x, writing it as a single fraction. That's going to facilitate my next step. So I'm going to rewrite the original expression. But now I'm going to replace that numerator at y plus 1 over x with this expression. It looks bigger, but it's simpler because it's a fraction, not a fraction plus a thing. Now I'm going to use the divide by a fraction property. It's multiplying by the reciprocal. So my numerator is xy plus 1 over x, that fraction that I got here, times the reciprocal, y over x, of the denominator. Now I can multiply those two. Upstairs, I'm just going to write it with parentheses first. xy plus 1 times y. And then downstairs, x times x. But I can distribute upstairs to get xy squared plus y, and simplify this downstairs just writing it as an exponent. And that's it, because there are no, there is a common factor upstairs. We could have left it like this and really like this too, but there's nothing to remove. There are no common factors upstairs and downstairs.